Wolfgang Hönig will be recording. We'll be talking about the Crazyswarm. So Wolfgang is a long-time Crazyflie user. He got his first Crazyflie in 2014. Still has a Crazyflie 1 around. He did his PhD at USC, and we had the opportunity to work together this spring, when Wolfgang joined the team for a couple of months in Malmö. We had a good time and did a lot of awesome stuff. So right now he's an independent junior research group leader in TU Berlin, working on having a lot of Crazyflies flying in close proximity. So I will give the stage to Wolfgang, and I will have a look at the chat during the presentation. Wolfgang, the stage is yours.
All right. Hello, everyone. Great to be here. And I will be talking about the Crazyswarm today. And since we are celebrating 10 years of BitCraze, I think it's fair to just start with a little bit of history. So once upon a time, about 6 years ago, there were actually very few research labs that were able to operate more than 10 robots. And there's many reasons for that. One is, of course, the cost. Maybe I should enable my video. So one is, of course, the high cost of a single robot. It is a lot of engineering effort. But there's also one other aspect that frequently gets forgotten, which is about reliability. So if you do some experiment with your Crazyflie and you have a success probability of 9 out of 10 times it works perfectly, but 1 out of 10 times it doesn't. Then once you go to just 10 robots, your probability that you succeed will be only 35%. So if you want to operate many robots, you really need to be very reliable. Nevertheless, in 2015, here's an example how it looked like. So that is some work I did. I believe it might be the first research work where we had multiple Crazyflies flying together. In this example, 6. And you can see that the quality is very different from what we know today. So in particular, the drone in front here was supposed to actually kind of hover in place, but instead it was shaking around a bit. Now, just about 1 year later, in 2016, which means 5 years ago, we asked the question at USC what it would take to fly roughly 1 order of magnitude more quadcopters. And the result of that question was a research project called the Crazyswarm. And here's how the video looked like. So we have in total 49 Crazyflies that can be controlled very precisely. So you can see there's no more shaking as in the video before. You can fly relatively fast compared to what we did before. And even though those 2 demos were centralized, we actually also had a decentralized demo here where we ran some algorithm on board each drone that would avoid James, who's walking here. And we also had some kind of demos on how to do those sort of formation changes. A few years later, we also extended that work to heterogeneous teams. So today, I split the talk in 2 parts. So in the first part, I will present in a little bit more detail how the Crazyswarm actually works, who the users are and what they do with it, and then also what the plan for the future is for the Crazyswarm. Then we can take a fairly short break, depending how we are on time. And then the second part, it's a little bit more tutorial or workshop style, where I demonstrate how to use a Crazyswarm for typical applications. Okay, so let's start by how the Crazyswarm works. So in particular, the system architecture is such that we have a bunch of components, which I will describe now briefly, and then we jump into a little bit more detail for some of the really important parts of the components. So first of all, there's a tight integration with motion capture systems, in particular Vicon, OptiTrack, and Qualisys. And we have our own custom object tracker that allows us to track so many crazy flies independent of the official software. And I will talk a little bit more how it works later on. In order to make it fast enough to serve so many, we had to optimize quite a bit for latency. And so we did that by changing the radio protocol a bit. And in particular, we introduced one-way data flow or broadcast communication. And we also implemented everything in a native language, specifically C++, in the backend to make sure that the latency of the whole system is as low as possible. And then finally, we also did a lot of work on improving the onboard autonomy. And that has something to do with the reliability statement that I made at the beginning. You can only fly that many if you improve the reliability, which also means that you need to have more autonomy directly on board of the different quadcopters. And at the beginning, that was kind of a custom, pretty hacky firmware, but nowadays, it's all in the official firmware, and you can just fly with the latest released version. From a user perspective, you actually don't need to know a lot of these kind of technical details, because you can script in the Crazyswarm just using Python, which has an API that is optimized for swarms. So we will see some examples later on what that means. And we also have a lot of interesting tools that are just helpful to interact with the swarm. So you can, for example, check what the health status is in terms of the batteries. You can reboot or flash all the crazy flies. And we also have support to simulate very efficiently. Okay, so now I want to talk a little bit more in detail about some of the aspects. So the Crazyswarm was initially made for Vicon motion capture system, but now it actually also supports a wide range of different localization systems. And so earlier in the workshop, you have already heard about the Lighthouse and LPS system, which is great because the initial infrastructure cost is really low, and also the estimation itself is, of course, decentralized on the robot. On the other hand, motion capture has a pretty high initial cost, but then the cost per robot is very, very low because you just need to buy a passive marker, and you get a very high accuracy, typically below 1 millimeter. Now, it turns out that Lighthouse and LPS are, of course, also supported, but we didn't put in quite as much effort to optimize for it. So really still the primary focus, at least for this talk and for the Crazyswarm, remains to give a great experience if you do have a motion capture system. Now, motion capture sounds nice because it seems to solve a lot of problems that we have in robotics. But in practice, it actually turns out that there's a lot of challenges ahead if you want to use a motion capture system for 50 robots. So the first very obvious one is that motion capture is a centralized approach. So you have typically one computer that runs some software from the vendor, and that does all the tracking of the object. And then you need to communicate with that computer, and that computer needs to communicate with the camera. And we also have to send all the data to the crazy flies. So in order to reduce the latency, what we did is actually implement the whole thing in one big C++ application, which allows us to have very low latency and few data copies in between. However, the Crazyswarm is also using ROS, which stands for Robot Operating System, under the hood. And this kind of single application is actually kind of an anti-ROS pattern. So it's not typically to do that. And we had to do some workarounds to still make it feel like using the ROS ecosystem well. And the second thing we needed to do, as I mentioned earlier, was to optimize the low-level communication quite a lot. Now, the second challenge with motion capture system is actually that they're optimized for a very different use case than what we had in mind. So typically, motion capture systems are designed for one of two areas. The first area is for tracking humans. So for example, to help with animation movies or to do some sort of athlete analysis. And the second use case is rigid body tracking, like we do, but typically very few rigid bodies. So maybe like 10 or 15. And typically those rigid bodies are also very large, which means you can put a lot of markers on them with unique configurations to make sure that the software can track it. So because the Crazyswarm is so small, we had to do object tracking ourselves, and we have our own library that can do that. So how does it look like? So we support two different modes for rigid body tracking. The first mode is tracking the pose of our robot. The pose just means the position and also the orientation of our robot. And that's the original version that we always had. It uses under the hood an algorithm called iterative closest point. It is pretty greedy, but seems to work fairly well. And then the second, slightly newer approach is pure position tracking. And in that case, you can actually only have a single marker, which we typically put on top, versus 3 or 4 markers for the pose case. And that uses under the hood optimal assignment or Hungarian method, if you know that algorithm, which is actually optimal and not greedy. Now, in both cases, we also have some filters. So we track frame by frame, and to reject outliers, we have some settings about the maximum acceleration, velocity, and angular velocity. And unfortunately, we are also required to know a rough guess of our initial position. Now, if we want to compare them, I would say that because the pose estimation uses this greedy algorithm, it is in general less robust to motion capture systems that maybe have a lot of spurious markers appearing. And of course, it needs more markers. On the other hand, you get as pro that you can really track the full pose, of course. Now, the position tracking is much more robust because of the optimal assignment. However, because you can only track the position, there's no way to measure yaw directly. So you do need some movement in X and Y to recover yaw. Typically, you can still hover in place for at least half a minute without any issues in that mode. Now, to give some more details on the swarm management tools, we have this little Python script, which is just called chooser, and it shows you all the Crazyswarms that you own and roughly how you would place them in your work area. And then you can use it to just select or deselect Crazyswarms that you want to operate on. And then for the selected ones, you have a few buttons at the bottom. So you can, for example, check the battery status, the version. You can turn it on and off. And you can also flash a custom firmware if you need to. Now, in terms of simulation, that's actually very interesting because when a user writes a script, the same script is used for both physical robots and the simulation. And you can just run it with a --sim in order to get a simulator. We have multiple visualizations of it. Here on the left side is one screenshot of like the 3D visualization, which will show you exactly how they would fly if you would run it. Now, the nice thing about that is that there's no ROS dependency here, and you can actually run it on Linux and Mac, potentially also on Windows, but we never tested that. And the simulation itself under the hood uses actually a software in the loop framework. So we do have Python bindings for relevant parts of the firmware, especially the trajectory planning part. And we execute the exact same code for the simulation for this part. Now, our simulator is much, much faster than what you would get, for example, with RotoS or CrazyS, which is a default aerial vehicle simulator on ROS, because we do not attempt to simulate aerodynamics. So we basically just show you the set point, and we can warn you if there's like sudden jumps in the set point, but we don't attempt to really simulate all the rigid body dynamics or interaction between drones. So you get near real-time performance, even if you simulate 50 crazy flies. Okay, I think it's also interesting to look at the Crazyswarm more from a software architecture perspective, because there's actually some components that I believe are very useful in general and for other robotics projects. So here's how it roughly works. So we have a few low-level libraries. The first important one is called lib motion capture, and it basically provides a unified API to the major motion capture SDKs. So specifically Vica and OptiTrack Qualisys, and also VRPN for other systems. And this one is written in C++. Now, lib motion capture can either output a point cloud of all the markers, or it can output already the rigid bodies if you decide to use the mocap's official software for tracking. If you pick the point cloud, we have another library called libobjecttracker, which does all the frame-by-frame tracking and outlier rejection and so on, which then would also output the rigid bodies. Now, on the other hand, we also have a low-level library called Crazyfly CPP, which is also written in C++ and communicates directly with the Crazy radio. And it has all the knowledge about COTP and high-level APIs to use it to send set points, to set parameters, and so on, similar to the Python library. And that one is used by two binaries. One is the Crazyfly tools section, which gives you a command line interface to the Crazyfly, also written in C++. And the other one is a Crazyswarm server, which combines everything written in C++, but relying on the robot operating system. Now, Crazyswarm server is the one that gives you the ROS API that you can use. And we simplified the ROS API with a Python interface, which we call PyCrazyswarm, which also includes the simulator. And as a user, you can either use that simplified interface, or you can, of course, also use directly the ROS interface. Now, one thing that is really interesting here is that over time, we actually spun off a few projects that we believe are very relevant for other people. So most notably, we have motion capture as a Python package now on pip. So you can just pip install it. It uses directly lib motion capture using PyBind 11 under the hood. And we also have a separate ROS package for motion capture tracking that gives you lib motion capture and lib object tracker for other kinds of robots, if you're interested. This one also already has a port, a partial port to ROS2. Okay, so now we looked at what the Crazyswarm is and learned a little bit about the architecture. So let's maybe dive into how people actually want to use it and using it. So for that, I looked about maybe 2 weeks ago how the paper is cited, and then I found out on Google Scholar that we have 199 citations, which is great. And then I went ahead and looked at all 199 of them. And so it turns out that out of the 199, 57 are actually users that do some cool research, and they try to validate it, and they use the Crazyswarm to do their validation. Now, 11 of those 57 are either co-authored by James, who co-developed as a Crazyswarm, or myself. So that leaves kind of 46 very unique research contributions by different people. And if you look at the age of the project, which is now at its 5-year anniversary, then we have basically 12 novel contributions per year so far, or 1 per month, which I think is really, really great. Now, I tried to look at the different topics of all of those projects, and of course, there's many different ones, so I just want to highlight maybe the range of what people have been looked at. And so one very large domain is actually planning. So planning is an area, motion planning, which I also worked on. So it's in particular designed for that use case. So there's no wonder that we have nearly 20 publications just in this area. There's also quite many that look into different kinds of state estimation and just use the Crazyswarm for example, for relative state estimation for validation. There's a bunch of papers that just look at control with single robot and swarm control. And there's also a lot of people who actually express their art using the Crazyswarm, which I find interesting because it means that the framework is simple enough so that people with maybe less engineering background can actually use it successfully. But it doesn't end here. There's many other exciting topics. So, for example, machine learning in just the last couple of years has been picking up quite a lot, where inference is also done directly on the Crazyfly and sometimes off board. There's some interesting papers in software engineering, namely one that looked at the quality of open sourced research code, and the Crazyswarm got pretty good marks in that survey. Virtual reality, optimization, and then things like target tracking and exploration, teleoperation, and resilience, just to give you some examples. And so you see all those funny numbers at the end. Those are all hyperlinks, and they're listed at the end of the presentation. So you can look at the papers if it's in your area of expertise or interest, and see what people have done and used it for, and maybe it can be inspiring for you as well. Now, I also looked at some other statistics on who is using it. So I looked a little bit by country, and there's still a large, I'd say, bias towards the US with the majority, but we see that we get more and more users now also from China and other Asian countries, and also more users in Europe, which is great. And if we look at by publication type, it actually turns out that a lot of really high quality publications are done with the Crazyswarm. So we have a really large fraction, or actually journal. There's a number of PhD theses that use it. Mine is included here, but there's a bunch of others now as well. And also a lot of great conference papers, of course. And now I just want to give you one example, because there's 50, it's too many, but this is one example I really like, and the community liked because it got nominated for the Best Paper Award in Multi-Robot Systems in 2019. And I think I will just show you the video because it speaks for itself. So I would say that the work here is kind of a combination of art, but also formation control. And so they do a lot of different kind of examples on what is possible. And this is my personal favorite part because it is crazy fast. Like in most videos, the Crazyfly is used, even if it's not a swarm. It moves fairly slowly, but in this case, it is really fast. And it's, in my eyes, very impressive. Now, one word of caution here. That work was, according to the paper, inspired by the Crazyswarm, but doesn't use it off the shelf. So they might have done some additional extensions to get it work so nicely. Okay, so now we looked at what the users do, and we had 57 papers out of 199. So we have over 140 left that I didn't talk about yet. And so some of them are just survey papers talking either about swarms or aerial vehicles or in that area. Some are, I would say, just unrelated. They cited the Crazyswarm, but there was maybe no real need to cite it at all. But then the majority of the papers in the 140 category actually use it to motivate mostly their own work. So the Crazyswarm is used, quote unquote, as a bad example that needs to be improved. And the most common criticism is, of course, that it's optimized for motion capture systems and that it's therefore kind of unrealistic for what we want to do. So that is, of course, very valid, and it's also common in the research community to cite papers to motivate your own work. But it's also important to remember or note that we do support decentralized operation. And so that's kind of one motivation for my talk today to clear that up. Okay, and that also motivates me to look into the outlook. So what are we planning to do? So first of all, I want to reiterate that I think all of our motivation is that we want to go away from this like manual operation and highly predictable lab settings to get swarms that can operate autonomously, ideally in unpredictable and unknown environments. And I still believe that even though the Crazyswarm is optimized for a motion capture system, is very valid to achieve this goal. So in particular, the focus that is ongoing right now is the following. We are currently looking at 3 categories: robustness, distributed operation, and heterogeneity. So robustness is something I talked about at the very beginning already. It is there to, it's really important to bring more onboard autonomy into the system in order to increase robustness. And that is something that we always have done as part of the Crazyswarm project and that we're planning to continue doing. On the distributed operation side, I think an important push here is to also improve the documentation and examples, because we actually support distributed operation fairly well already, both in terms of the localization system, but also in terms of execution. And I will give you an example later on in the second part of the talk. And then also long-term, I think we really need to move more into monitoring and management of swarms. If we have fully autonomous swarms, then maybe we don't have a central computer sending commands anymore, but we want to make sure that we keep an overview of which crazy flies are healthy and which need maybe maintenance and so on. Finally, I believe ROS has a lot of disadvantages, of course, but one of the advantages is that it allows to integrate with many other robotic systems. So to work in heterogeneous systems with different ground robots or different flying vehicles, for example. And so for that, we kind of work on better simulation to allow heterogeneous teams, and maybe also physics-based simulation to really look at what happens if you have different kinds of robots in your environment. Now, more concretely, what we are planning to do short-term is the following. First, we are about to switch to Crazyflie Link CPP, which is something that I developed while being at BitCraze at the beginning of the year. It's a new native backend that will allow much more robust communication and fun things like uploading trajectories while you're flying. We work on a new simulation that supports distributed algorithms better. And after that, there will be a port to ROS2, which will likely be a slightly breaking change, at least in terms of the configuration files that we have. And then I'm also looking into the physics-based simulation and, of course, use of the Crazyswarm in the classroom for master students. And with that, I think we can take a fairly short break. So maybe 2 minutes, I would say. And then we start with the tutorial style second part of the talk.
So Wolfgang, while we're waiting, maybe we could do one of the questions from Jonas.
Sure.
Yeah.
What is the question?
Yeah, so the question is, what is the main benefit of using ROS? And also, is fighting the architecture with the anti-pattern of C++ monolith worth it?
I think there's two major benefits of using ROS. The first one is the integration with other robotic systems. So once we move to more heterogeneous systems, then we can use ROS much more effectively. The second advantage of ROS is actually the ecosystem that it has, or the tools that it has. And in particular, it has really nice visualization tools that we also use for the Crazyswarm. And that helps the user to just see how everything works. Now, is the anti-pattern worth it? That's an excellent question. We started initially by trying to not have an anti-pattern, and it didn't work out. And then we did that. Maybe for the ROS2 port, we will reconsider that and see if kind of the underlying communication infrastructure improved sufficiently enough to follow the proper ROS guidelines.
Yeah, thanks.
Okay.
Yeah, let's continue.
Maybe we can continue.
Yeah.
And then take more questions later on, of course. Okay, so let's look at the Crazyswarm tutorial or workshop. And so I will just run you through kind of 3 examples that I think are most relevant. So what I'm not going to cover is kind of the initial setup. There's a lot of documentation online that you can look at that describes how to get it running. You will need to know ROS a little bit at least, and we mostly support Linux. And if you just want to do simulation, you can also use macOS. So once you have installed the Crazyswarm according to the documentation, then you can define your UAV type. And so I said it earlier already that we do support heterogeneous systems as long as they rely on the Crazyflie or Bolt as a control board. And so we already have predefined a few platforms, including the standard Crazyflie 2.0, 2.1, and then 2 bigger ones where we also have on our webpage the parts list if you want to build those yourself. And that is just configured in a YAML file, which includes things like, oh, are you using the big quad deck or not? What is like voltage warning? And how are the markers configured on your Crazyswarm? The second configuration file you need to adjust is just one that lists all the different UAVs. So here we specify the unique ID, which you have to assign using the official software, the channel it operates on, and then also the initial position. Now, the initial position is only used if you rely on motion capture or if you use the simulation. If you use the lighthouse, for example, that is not used for the physical robots, at least. And then kind of the simplest example, the Hello World example is really simple, just basically 6 lines. You just import the PyCrazyswarm package, you instantiate an object, and then you can say that you want to take off all your Crazyflies to a specific height, and that the takeoff should take 2 seconds. Then we have a special sleep function. So you wait 3 seconds and then you land again. And so if you run it in simulation, it looks like that. So you first select all of them, and then you run it with the --sim argument. And that was the matplotlib simulator, which you can choose. And if you run it physically, you just drop the --sim, and it would look something like that if you have the same number of crazy flies. Okay, so that example is maybe, a little bit boring because it doesn't do that much. So let's look at something a little bit more advanced. So the lines that are highlighted here are simply the ones that changed from the previous example. So we have one additional block, lines 4 to line 7. And what we do here is, while we're still on the ground, we load a trajectory from a file in line 5 and 6. And then in line 7, we just upload the trajectory to the Crazyflie. And that trajectory, it's in a loop, so that will be a different file per Crazyflie. And then we do the same takeoff, waiting, and then we have a new call that can start the trajectory. And so here's one example of one research project I had, which was about motion planning. So where we did some offline trajectory generation. We generated those CSV files, and then we ran it on real quadcopters. And that works in heterogeneous systems and in homogeneous systems, of course. Now, where should those trajectories come from? We do not have any tools inside the Crazyswarm project itself, but there's a lot of good tools outside the Crazyswarm that you can use and that use the same file format. A very simple one is a repository on GitHub called UAV trajectories, where you can, they have 2 modes. The first mode is just you give it a sequence of waypoints and a desired velocity and acceleration. And then you can generate a trajectory for one Crazyflie that just goes through the waypoints. And you can also plot it and look at like the velocity profile, acceleration profile, and so on. The second mode that repository supports is a sequence of time waypoint pairs. So for each waypoint, you also specify at which time you want to be at the point. And here's one very simple example. If you want for Crazyflie to move on a circular trajectory, you can just write a Python script that generates the sequences of time waypoint pairs using the equation of a circle here, and also putting out the time. And then you can do pretty cool demos. So that's something I did at Caltech maybe 1 or 2 years ago, where you have 3 rings. So we have one ring here, and then a horizontal ring in the middle. And they're actually kind of intersecting with each other and fly really, really close to each other. And that's also just done using single marker tracking. And you don't need a fancy trajectory planner as long as you make sure when you define your sequence that there can be no collision. Now, if you want to really work into multi-robot motion planning that's a little bit more automatic, that is pretty advanced and still very active in the research area. So there are, again, some references if you're interested. Luckily, some of them are open source. I added a few links here. Unfortunately, most of them are really like research repositories, so they're not well documented, not that well maintained. So it does require quite a lot of prior knowledge and effort, I would say, to get them up and running yourself. Okay, and so now I want to talk a little bit more maybe about a distributed execution, which I hinted on before. And so in particular, here's one example again from my own work, because I know it best. We had some distributed algorithm that was pretty computationally heavy. So in particular, it was a Monte Carlo tree search where we used multiple neural networks to kind of guide the tree search. If you run it on a desktop computer, it works pretty well, and you can, I think, get values at like at least 10 hertz or faster. But of course, doing Monte Carlo tree search and multiple neural networks directly on board the Crazyflie might not even be possible, or it would be at least a lot of engineering effort to do so. And so what we opted for instead is to try to emulate the distributed execution as realistic as possible by running on a host computer that has multiple cores, one process for each Crazyflie. And that process would then implement the Monte Carlo tree search and the neural network evaluation, and then send control commands at a fixed frequency to each of the Crazyflies. And so the Crazyswarm is mostly used still for the simulation purpose, and of course for the visualization of everything and for the swarm maintenance. And so here's kind of how it looks like. So now we're more inside the ROS world. So we don't only have our normal Crazyflie PyCrazyswarm import, but also a ROS.py import on line 1. And then we have some more ROS-specific code to just initialize our process, or in ROS terminology, it's called a node. And then we can instantiate our Crazyflie as long as we know its ID and a rough guess of the initial position, which is important, again, for simulation or if you use a motion capture system. And otherwise, you can just put in random numbers. And then we can just have one loop that has at its main body some complicated function, in our case, the Monte Carlo tree search, computes some sort of set point. For example, position could be something more advanced, like a set point that includes velocity and acceleration. And then at a fixed rate, we just run it and then set position. And if we want to execute it, we just write ROS style a launch file. And the launch file basically allows us to spawn all the different processes we need automatically, which is like a common method in ROS. And so all it says is that our nice example 3 scripts that we have, we want to run once for our Crazyflie number 1. And we also want to run it again for our Crazyflie number 2. So if we have more than 2 Crazyflies, it would just copy and paste the block a bunch of times to get more processes. And now running the system is actually very easy. You would just run ROS launch, Crazyswarm run launch. And if you don't add any flags, that would run it on the physical hardware. And then if you run it with that sim equals true flag, then it would actually run in simulation. That's currently like a pull request, but so it's not in the very latest version, but it should be merged in the next 1 or 2 weeks. It's fully tested. It just misses some documentation for it to be merged. Okay, and then I just want to give you maybe an example on how the flight looks like. So this is one very simple example where we had 5 robots, and it was a game in an adversarial setting. So we had 2 teams, a blue team and a red team. The blue team tries to go to the green region, and the red team tries to prevent the team to do that. So I just play it again so you can see it. And the prevention happens by trying to kind of move in close proximity of another robot. And so that was something that we could run on the host computer, I think at 10 hertz using the Monte Carlo tree search and the neural networks. And I don't think it would have been possible to do on board the drones themselves. Okay, so that was kind of my brief tutorial about the Crazyswarm to kind of show you a little bit what you can do, and hopefully also convince you that it's actually fairly easy to do things that seem intuitive to humans. That is how it's designed, and that's what we try to achieve. So let me maybe conclude so that we also have some more time for questions at the end. Okay, so the Crazyswarm is a very versatile open source framework for aerial and heterogeneous swarms. By heterogeneous, I mean right now everything that's in theory supported with Crazyflie or Bolt platform, so different sizes of quadcopters. It supports centralized and decentralized operation and actually many different localization methods. So we support motion capture very well. We support Lighthouse, LPS, anything that has VRPN. You can also just fly using your flow deck if you want, anything you like, anything that we have seen basically also early on the talks. And unlike the common belief that it's purely centralized and kind of out of date, it's actually moving very much towards supporting decentralized operation better. And I think it's therefore also interesting in those areas. And we have seen that it's already widely used in research. So one publication per month is quite good. And that there's also many domains where it's used in. Now, if the Crazyswarm is not what you're looking for, then I still have some good news for you. There might be some interesting parts that you can still use for your own purposes. So first of all, I believe tracking is always a problem in robotics, not only flying robots, also ground robots. And therefore, we made an effort to have separate solutions for that. So if you're in C++ world, you can use lib motion capture. If you like Python, you can use pip motion capture that works on Windows, Linux, and Mac, by the way. If you like our frame-by-frame tracking, there's our lib object tracker and also our standalone ROS stack that can allow you to use it. Now, if you're not into that, then you might be actually interested in the Python bindings. And the Python bindings for us are mostly a way for simulating the Crazyswarm. But in the past couple of years, I've actually also used them for many other interesting things. For example, if you write a new controller, it speeds up the time until the time for getting it to work, because you can actually test it in simulation before you do a lot of crashing flight tests, which is great. If you work on state estimation, I have used a prototype for the Python bindings for the EKF, so you can actually log real data from flights and then just tune or change your EKF on your computer and just use the simulation and the bindings to see how it would look like with your changes and do nice quantitative comparison and analysis. And then finally, to my knowledge, the Crazyswarm is still maybe the easiest way to operate one or more Crazyflies in MATLAB. So if you're a MATLAB person, just use the ROS toolbox on the same or different machine and use the Crazyswarm in order to talk to the robots, and you can basically do almost everything. That being said, this year we also finalized the merge of Crazyflie ROS and Crazyswarm. So Crazyswarm is now that solution you should move forward with, and we will put an effort in to make it also working nice if you just want to operate a single Crazyflie. Yeah, I also want to take some time to acknowledge the many people who made it all happen. So first of all, of course, James Price, who was the original co-author and is still a very active maintainer. So if you have an issue or go on GitHub and have a discussion, he will frequently respond and help you out. And so will I. And then we also had a lot of PIs helping us at the different universities where the project was active. And then lastly, BitCraze also has been a lot of help, in particular with the ongoing effort of moving features from our own proprietary branch back into the official firmware, getting it all nice and clean, and also tested. So the Crazyswarm is now actually part of the Crazy testing lab and will be tested, I believe, nightly or weekly, so that it keeps running smoothly. Yeah, and I encourage you to use the Crazyswarm, because if you don't, you might get something like in the video here, which was a very early prototype of the Crazyswarm in 2016, where we made a threading coding mistake, which caused a dramatic crash, and we had to clean up quite a lot afterwards. You can find more information on the webpage, and you can, of course, also reach out via email to me. Thank you very much.
Thank you, Wolfgang. Thanks for a nice presentation and a nice footage of a crash. So we're running a little bit over time. The next presentation is in 6 minutes, and it's Jonas, so it's going to talk about the CFlib. But we have one question that maybe we can do quickly. That is from Atay. Do the trajectories also include yaw, or is it just position and yaw is kept constant?
The trajectories also support yaw, and it's like the other components, an 8th order polynomial.
Yeah. Thanks a lot.